good afternoon. Welcome to the last seminar before the Christmas, I guess. Today's speaker is Matteo Cinus. I'm not sure if I'm pronouncing it correctly, sorry.
I will pronounce it again.
Okay, so thank you, Matteo, and please start.
Okay, so thank you. First of all, thank you for inviting me to give this talk. Sorry again for the delay, and thank you for being here to attend the talk. My name is Matteo Cinus, and I'm a PhD student working at Nicolaus Copernicus University in Torsion. You might think is another university named after Nicolaus Copernicus in Poland, but actually Torsion is the city where Torsion was born. So maybe the university named after him is actually carrying a particular meaning. As I said, I'm a PhD student working under the supervision of Andrew Kema and Krzysztof Bolenko. So this is the outline of my talk. I don't know if it's a problem that this is showing. I don't know how to hide it. Okay, perfect. Okay, so this is the outline of my talk. I will start by introducing cosmology as a science today and the standard model of cosmology. Then I will talk about the alternatives to the standard model of cosmology in the form of modified theories of gravity and the reasons why modified theories of gravity are being considered today. I can probably leave this so that you can see my face even though it's small. Okay, so then I will discuss the geometrical extensions of general relativity, and because I want to talk about torsion, which is a geometrical feature of the spacetime of our spacetime, of the spacetime that we can use to describe general relativity or to generalize it. And it's a feature that has been studied very early on, even by Einstein. The reasons for which it is studied today are the same reasons it was studied back then, but also for new reasons. And I try to give you an overview, a quick but comprehensive overview on that. And finally, I will focus on geometrical signatures of torsion. And in particular, I want to, in our work, to stress on those particular signatures that cannot be reproduced by any other model with dark energy, for example, and therefore are strictly signatures of torsion. So let's start by introducing cosmology. Sorry. So once it was a very philosophical and metaphysical discipline, but nowadays cosmology is the science that that studies the universe, and the universe is shaped by gravity. The current understanding we have of gravity is based on Einstein's theory of general relativity, which is a rather recent theory published in 1915, which completely changed our understanding of gravitation. In fact, before that, and still to some extent today, we thought and we still think of gravity as a force acting on massive objects. But when we want to study the universe as a whole, we have to think of gravity as a physical law that relates the geometrical properties of the space-time to the matter and energy that fills the universe. This is probably something you already know, but I wanted to stress on the fact that that general relativity is a geometric theory of gravity. And since we are interested in a geometrical property of the spacetime such as torsion, this is important to remind. Okay, so the standard model of cosmology is based upon two theories, the standard model of particle physics and Einstein theory of general relativity. Here there is a question mark next to the standard model of particle physics because in principle we don't need to have it as a separate assumption because the validity of the standard model of particle physics is is ensured by one of the postulates of general relativity, which states that locally the laws of special relativity are still valid. And therefore, from the laws of special relativity, we can recover all the results from the standard model of particle physics. Okay, so after basing our cosmological model on general relativity, we have a model that is very difficult to deal with, very general. So in order to constrain the degrees, for example, of homogeneity and isotropy in our model, we have to make some assumptions. Historically, they didn't have any data to support any kind of assumption, so they just went for the easiest possible option, which was to assume the cosmological principle, which is based on, which is a generalization of the Copernican principle, which states that in the universe there is no privileged direction or point, and therefore we recover the assumption of perfect homogeneity and isotropy. The second assumption is about the matter content of the universe. In fact, since the early stages, new data became available, and in order to accommodate this data, they had to introduce new parameters in the model, namely dark energy and dark matter. Dark energy and dark matter are in fact the two entities, the two things that the two energies that are dominating our universe. At least today, it is believed to be so. With the stars, with the observational universe, with stars, planets, and even us constituting only a very small percentage of it. So with dark energy and dark matter, we have all the ingredients of the standard model of cosmology, which is called the lambda CDM model, and where lambda stands for dark energy, for a cosmological constant in the Einstein's equation, or dark energy, and CDM stands for cold dark matter. Here I wanted to also point out that dark energy is associated with the vacuum energy density, and which is predicted by quantum physics. The problem is that the value predicted by quantum physics is quite small. Like there is a disagreement between the theoretical prediction and cosmological observations of 50 to 120 orders of magnitude. So a big disagreement. So the nature of dark matter and even less that of dark energy are well understood today. So in order to try and explain them, several models that generalize general relativity have been considered. So these models have been proposed not only to address the mysteries in the universe, such as dark energy and dark matter, but also processes like inflation, or to help and construct a theory of quantum gravity. In general, considering these theories can also be useful to better understand GR and its assumptions, or to test GR. In fact, it's important to try and subject the GR as any theory to new tests in order to increase to corroborate the theory or to uncover new physics. Okay, so the general relativity is based on Riemannian geometry. So let's start with some definitions. Here I will be using the words manifold, the terms manifold and space interchangeably, because a manifold is just a topological space, or without involving topology, we can just say that it's a structure that we use to describe our space-time. When the metric is positive defined, we have a Riemannian manifold. I hope you can see my pointer moving around. And but in general, the metric of general relativity and of special relativity is not positive defined. Therefore, we have in general a pseudo-Riemannian manifold. In particular, the metric has a signature minus plus 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 in special relativity in GR, or plus minus minus minus, depending on your signature choice. And therefore, the most general space that can be used to describe geometrical generalization of GR is a Lorentzian manifold. Here, let me point out that in principle, by this definition, Riemannian manifold doesn't have anything to do with GR. And a pseudo-Riemannian manifold is a much more general object. So we don't need to explain GR as well. Sorry, I was sick all over the weekend, so I'm afraid of coughing, and that's why I'm drinking to try and not inflammatory too much, let's say. Okay, sorry. So we have Lorentzian manifolds, and in order to characterize them, we need to jump to quantities: the metric, and the connection. The metric is what allows to define angles and lengths on our spacetime, and it allows for the definition of a scalar product. While the connection is what allows us to move around on the manifold, and it's what allows for differentiation on our spacetime. From these three quantities, we can write these three geometrical entities: non-metricity, curvature, and torsion. And here I would like you to note that the curvature and torsion are solely dependent on the connection and not on the metric. And in particular, torsion is defined as the anti-symmetric part of the connection. So what are these three quantities that we introduce? So curvature is associated with a rotation of a vector when transported along a closed curve, as in the first picture in the left top corner. Torsion is associated with a non-closure of a parallelogram constructed by parallel transporting two vectors along each other. So it's associated with some twisting of the spacetime. And finally, non-metricity is associated with the variation of angles and lengths of vectors when parallelly transported along a curve. So, as I said before, the metric is what helps us define, allows us to define lengths and angles. So when non-metricity is conserved, so it's 0, lengths and angles are conserved as well. But when the non-metricity is non-zero, these quantities are no longer conserved. And here in this picture, we can also see what the connection is doing, is allowing to move our vectors around on our curved spacetime, or in particular terms, is called parallel transporting a vector along a curve. Okay, so on these three quantities, we can define a whole series of spaces. And the most general one is called the metric affine space. The most particular one, when all these three quantities are 0, is the Minkowski space, which is the space of special relativity. When we take a Minkowski space and we put curvature on it, we found the space of GR, a Riemann space. And here I would like to point out that there is a little bit of confusion in the notation, because as I said before, Riemannian manifolds are something that doesn't have anything to do with GR, and pseudo-Riemannian manifolds are things more complicated than what we need for GR. But the spacetime of GR is still called a Riemann space. So I'm sorry, it's probably causing a little bit of confusion between let's say the more cosmological approach and the more differential geometry approach, but that's how it is. The spacetime we're interested in is a spacetime with both curvature and torsion, and it's the Riemann-Cartan space. And here I wanted to point out that there is a particular case where only torsion is allowed, which is the Weizenbock space. So the first time in history that a space with torsion has been considered was in 1922 by Elie Cartan. And the theory he worked on then became known as the Einstein-Cartan theory, because Einstein himself got involved with the theory in 1928 in his first attempt to unify the two known forces at the time, gravity and electromagnetism. In fact, the weak and strong solar forces were still unknown at the time. So this first attempt failed, and Einstein continued working on his unification theories and by doing that, he gave birth to teleparallel theories of gravity, which are theories where only torsion is allowed and curvature is taken to be 0. And therefore, these theories are defined on our Weizenbock space. Okay, so the important thing about the Einstein-Cartan theory is that it might be a little bit complicated, but when going from special relativity to general relativity, so when including gravity in the picture, it's there is a symmetry which is called invariance under the Poincare group of transformations, which is lost. And in order to, but this particular invariance is recovered in the Einstein-Cartan theory, and this is recovered by allowing for torsion, and in particular by relating torsion with the spin. In fact, the Einstein-Cartan theory is not only important historically, but in our case, it's also important because it gives us a feeling of what the torsion could be associated with. So the theory of general relativity is locally invariant under Lorentz transformations, and the full, as I said, the full invariance under the Poincare group is restored only in presence of torsion. So as much as a property of matter such as the mass is associated with curvature, another property of matter such as the spin is associated with torsion. Okay, models with torsion have also been considered in lately to try and solve some problems related with both the early and the late universe. In the early universe, a minimal coupling between the torsion tensor and Dirac spinors can cause a spin-spin interaction, which is significant at the very high energies we have in the early universe. And it has been shown it can prevent the formation of a Big Bang singularity. So when the universe is contracting, it contracts to a finite scale factor, and it starts expanding back. And this phase of expansion that follows the contraction, it's actually a very fast expansion that is very similar to inflation. In the late universe, torsion is instead being associated with dark energy, in the sense that it has been shown that it can mimic the effect of dark energy, and therefore explain the present phase of accelerated expansion we are seeing. Okay, so an important thing to say about torsion is that it can mimic a lot of properties that are of models with scalar fields or dark energy models. And therefore, in our work, we were particularly interested in those in finding the observational signatures of torsion that could not be explained by any other model with scalar fields or dark energy. And in particular, since we are interested in observational signatures, let's start with talking about light propagation. Let's start with light propagation in an Euclidean space. So when light is propagating from point A to point B in an Euclidean space, it does so by following a curve that is both the shortest and the straightest line possible. However, when generalizing this concept to curved spacetime, the shortest curve is associated with an extremal curve, which is described by equation number 4, and the concept of a straight line is generalized by autoparallel curves, which are curves whose propagation vector is parallelly propagated along the curve itself, and those curves are given by equation number 5. So this quantity in curly brackets here in equation number 4 is a sum of first derivative of the metric tensor, and in general relativity it's called the Levi-Civita connection. However, when considering more general spacetimes, or for example spacetime with torsion, this quantity is no longer a connection, while in equation number 5 we have a connection. So these two quantities differ, and these two equations therefore differ, and therefore in presence of torsion, autoparallel curves and extremal curves are no longer the same thing. Okay, so now let's talk about how light propagates. And astronomical observations are based on the geometric optic approximation of Maxwell equation, which in fact tells us how radiation propagates. So we have that information is conveyed to us on light rays that travel on null curves. So the definition of null curves is given in equation number 6, and these null curves in general relativity are called null geodesics. The equation number 6 can be rewritten by using the definition of propagation vector here, and it can be rewritten in a form that is very similar on the left-hand side to the equation number 5 here. However, on the right-hand side, we have something that depends on torsion. And therefore, we have this, that not only the two definitions in the other slide, but also this other definition of null curves they are all in disagreement. And in general, we have that in presence of torsion, null curves are not null geodesics anymore. Okay, so however, the result of general relativity, therefore that null curves are geodesics, autoparallel, and extremal curves, as in GR, as I said, is recovered when torsion is totally antisymmetric. And this is true when the weak equivalence principle is required to hold. Okay, but in the most general case, this is no longer true, and torsion can be thought of pushing photons out of null geodesics, and therefore light does no longer propagate on autoparallel curve or extremal curves as shown in this picture here. So these three definitions are all different. Sorry. Okay, so now we can ask ourselves, how can torsion affect observations? And we can start by considering the distance duality relation, which is a fundamental law of physics that relates the luminosity and the angular diameter distance, as in equation 7. These two distances are two of the most often used when measuring structures, and they are both dependent on the geometry of the spacetime. So they are model dependent. Citing at least the core of the reciprocity theorem is the reciprocity theorem is another way of calling the distance duality relation. The core of the reciprocity theorem is the fact that many geometric properties are invariant when the roles of the source and observer in astronomical observation are transposed. So this is a very important tool for cosmology, and it lies at the heart of most cosmological observations. The distance duality relation, or DDR, here, just a compacted notation, it can be written in terms of the angular diameter distance RO or the galaxy area distance RG. And these two are related in equation number 8. These two distances are defined as the square root of the ratio between the cross-sectional area at the observer and the solid angle at the source. And the P and P prime here are the connecting vectors that are connecting the light rays in the light bundle that diverge at the observer and that converge at the observer, for respectively for P and P prime. Okay, so let's take a jump back to Euclidean spaces once again, and to talk about the concept of parallelism. In fact, two curves that are parallel in Euclidean geometry, they stay parallel to each other. But this is no longer true in presence of curvature in general on curved spacetimes. And how do neighboring curves evolve is given by the geodesic deviation equation, which is the equation in number 10, where k beta and k gamma are the two propagation vectors for two neighboring curves. P is the connecting vector between the two curves, and R is the Riemann tensor, which encodes all the information about the curvature of the spacetime and therefore tells how the curves how to evolve. So we can, by definition of connecting vectors, we can write two geodesic deviation equation for P and P prime that I showed here in this picture. So for the light bundle that diverge at the observer, P, and the light bundle that converge at the observer, P prime. So considering the curve, sorry, once again, back to the picture, the curve SGO or SO that connects the source to the observer, we can take the difference between the two geodesic deviation equations And by means of the Riemann of the symmetries of the Riemann tensor, we can show that this result is equal to 0. So now we can put the derivative on both sides, and we have that the left-hand side is equal to a constant. This constant can be evaluated at both O and G to give equation number 12. Equation number 12 is a general equation that is valid for any pair of connecting vectors P and P prime, and therefore we can choose them to be any pair of such vectors, such as, for example, they are orthogonal at both O and G. With this choice, we can recover the equation number 13, which is relating the cross-sectional areas and the solid angles. And therefore, by remembering the definition of RO and RG, we can recover the distance duality relation in terms of them. Okay, this was the case in GR when torsion was taken out of the equation. It was barred out in the previous slide. But now, in presence of torsion, we have the geodesic deviation equation shows dependence on torsion in these two terms. And there are also another few terms hidden in the generalized form of the Riemann tensor G. Therefore, when we can still take the difference between the geodesic deviation equation for P and P prime. And what we obtain is something like this, which is very ugly, I know. This is just to show how the actual calculation looks like. And actually, for example, in the case when torsion is totally antisymmetric, most of these terms cancel out, and the only terms that don't cancel out can be reabsorbed on the derivative of the left-hand side here. However, when torsion is non-totally antisymmetric, there are some terms that don't cancel out and can be reabsorbed in a parameterized form in the function j of torsion here in equation number 18. This equation can be integrated all the way from equation 18 to equation number 20. And in the case that we studied in our work, which is a homogeneous and isotropic model with torsion, we have that J is positive, and therefore we obtain a first correction to the distance duality relation that is positive, this G of the factor here. A second correction to the distance duality relation, it comes from considering the distance duality relation written in terms of the luminosity distance. In fact, the luminosity distance depends on the flux, and the flux itself depends on B. That is it's a parameter defined here, and is a parameter depending on torsion. So when B is small, we can take the limit of this of the exponential, and we can write the distance duality relation in terms of these two parameters G and B that are related to the cross section, to the effect of torsion on the cross section of the light bundle G, and while B is related in fact to the flux. The deviation from the distance duality relation is usually written in terms of this parameter eta, and in our case it takes the form in 25. So when torsion is weak, so both G and B are taken to be smaller than 1, we have that eta can be written in the form in 26. So this is still a general form where we only have assumed the weak torsion approximation. And by considering a homogeneous and isotropic model with torsion, where torsion is given by the function phi of t, we have that two terms that here, these two terms here that define B, are given by equation 27. These two, when assuming a particular model, such as the homogeneous and isotropic model with torsion we considered, we have that we can integrate B and G, and we can show that B is proportional to phi, and G is proportional to phi squared. So in the limit of weak torsion, we have that the correction coming from the distance duality relation is smaller than the correction coming from the flux. And therefore, in the parameter eta k is proportional to only the correction with respect to the flux. Okay, so since the function phi torsion has the units of the Hubble parameter of the expansion rate, we can write the normal parameterization are based on taking phi to be proportional to the Hubble parameter. Here are some models that we consider in our work, and this is the distance duality relation they produce on the right hand side of on the right part of the table. So the deviation they produce on the distance duality relation can also be shown in this plot here, where we have assumed a value of eta to be minus 0.03, eta 0, sorry. So the value of the deviation depends on the choice of eta 0, but here, for example, we have negative values, which means that the distance, for example, the luminosity distance inferred in a universe with torsion will be smaller than the luminosity distance measured in a universe without torsion. Okay, since it is proportional to the expansion rate, and the torsion also affects the evolution of the scale factor, and therefore it also affects the transverse co-moving distance in equation 29. So the effect of torsion on observations can be measured in terms of the absolute apparent magnitude. And when considering standard candles, the difference in the magnitude between a lambda CDM model with torsion and a lambda CDM model without torsion, by equation number 30, where we have a corrective term coming from eta, so a correction coming from the flux, and another corrective term in delta D, which is a correction that comes from the scale factor. These two terms can be shown separately in this plot here with the dashed line and the dashed dotted line. And the overall effect is shown by the solid line. Okay, these effects can be seen to be rather small, but they are not negligible. They are small compared to the dispersion of supernova data, for example. But they are not negligible because when interpreting these results in a model with GR without torsion, this will lead to misinterpretation of the data. And for example, the change in the magnitude is negative. Therefore, supernovae would appear to be brighter than they actually are, and they would appear to be brighter than they actually are as the redshift increases. So that means that this result could be interpreted, for example, as an evolution of the source, which means that, for example, supernovae were brighter in the past. Okay, but this result can also be misinterpreted in terms of the Hubble constant. In fact, it could change the inferred value of the Hubble constant. It could be misinterpreted as a change in the inferred value of the Hubble constant. In fact, when we take the value of the Hubble constant at 0.3 at a redshift of 0.3, we have a value of the Hubble constant which is 0.4 higher. This kind of effect is qualitatively similar, although reversed in sign compared to a Hubble bubble, which is an effect that where the Hubble constant is locally smaller or can also be higher than the Hubble constant outside of the local universe. And so, for example, the Hubble constant inferred from low redshift data versus the Hubble constant inferred from high redshift data. And although the torsion is not the main candidate for a Hubble bubble effect, it is interesting to show that torsion could produce such an effect. Okay, so now we have seen some cosmological observations of cosmological signatures of torsion, but we can actually ask ourselves, how can we distinguish from the dark sector, for example, and in order to see what of these observational signatures cannot be reproduced by any model with dark energy. And we can say for sure, for example, that no matter how model with the dark energy is, it will never be able to explain any divergence from the distance duality relation. And therefore, the distance duality relation itself, it's a very important tool to study the presence of torsion in the universe. Another way of detecting possible deviations from the Riemannian geometry is to use the Clarkson-Bassett-Lu function, CBL function, which is defined in equation of 33 in terms of the Hubble parameter and the transverse co-moving distance, which are both quantities that I have already mentioned before. So dependent on how H and D are measured, are inferred, the Clarkson-Bassett-Lu function can give us a value of 0 or not. So for example, here in this plot, we show that when distances are inferred from the angular diameter distance, so there is a consistency between the derivation of the value of the transverse moving distance and the Hubble parameter. We have that the CBL function is a 0. But when distances are inferred from supernova data, for example, so from the luminosity distance, the Clarkson-Bassett-Lu function is no longer 0. So I'm already the conclusions of my talk. When torsion is present, the distance duality relation in general is broken. And we have seen that this is no longer true. So the distance duality relation is still equal to 0. Not equal to 0, but the parameter eta is equal to 0 when torsion is totally antisymmetric. But totally antisymmetric torsion is a quite particular case. And for example, in the homogeneous and isotropic case we consider with torsion, the torsion tensor is not totally antisymmetric. So from an observational point of view, the observational constraints on eta are still not conclusive, but they are still consistent with eta equal to 0. So far there seems to be no torsion in the universe. Other effects that can show the presence of torsion are the change in the magnitude we discussed, that can produce small biases in the Hubble constant at low redshifts. So, for example, precise measurements of supernova at low redshifts can be used to study torsion cosmology. And finally, depending on how distances are measured, also the CBL function can be a potent tool to study possible deviations from Riemannian geometry. So in all these results are in our paper called Cosmological Signatures of Torsion and How to Distinguish Torsion from the Dark Sector, which was published on Physical Review D in 2020. So if you want to know more about these results, feel free to check the paper itself. So that's it for me. Thank you. Thanks for your attention, and sorry again for the delay. I hope I didn't go too far, and I actually managed to finish in time.